gases in the presence of disorder.
Thank you very much. Thanks the organizers for having me here. Okay, so I'll talk about some fairly recent work done in collaboration with a number of people. The first three are the group from Grenoble. I also worked a bit with a student from Bonn, Peter Hensler, and we have two ongoing projects, one with John Choker and with a graduate student of mine from the Technion. I'll talk both about Bose-Einstein condensate and cold Fermi gases, but I'll start with Bose-Einstein condensate. Maybe I first summarize some basic equations and outline the problem on the blackboard, because then I can refer to it later. Okay, so I start with the Bose-Einstein condensate initially in a trap in equilibrium. So this is the harmonic trap, the potential 1/2 m mass of the atom omega square r square. I write the equations for 3 dimensions, but most of them are good also in 2 and 1D. So initially the condensate is in equilibrium. I take temperature equals 0. Then the condensate wave function obeys the Gross-Petevsky equation. This is the trap potential, and this is the nonlinear term equal to mu psi. Mu is the chemical potential. Actually, in equilibrium, the wave function is real, so I can write psi cube, but soon I will discuss dynamics, then it will become complex. Okay. Nonlinearity is initially in the equilibrium. Nonlinearity is very important. Actually, the energy is dominated by this nonlinear term, because in the absence of interaction, in the absence of nonlinearity, all bosons would go into to the ground state of this harmonic trap, and the size of the oscillator would be simply square root h bar over m omega. I call this length A naught. But in experiment, the size of the condensate is much larger, because actually the size is dominated by interactions. So it means that the chemical potential is much larger than this energy h bar omega. And the size of the condensate is given by half m omega square r naught square. This is r naught. Equal to the chemical potential. So this length r naught is much larger than A naught. This is just another way of writing this inequality in terms of energies. Thank you. And as long as this inequality, this strong inequality holds, the Thomas Fermi approximation is a good approximation for describing the equilibrium shape of the condensate. Well, it simply means that one can neglect the kinetic energy and balance the potential energy of the trap against the interaction energy. So basically the the initial wave function, this psi of r, to a good approximation, it is simply square root mu over g, 1 minus r square over r naught square. So the density of the condensate simply follows the profile of the trap, and the shape is what they call inverted parabola. Okay, so that finishes the description of the equilibrium state of this condensate. I will discuss the problem of expansion of the condensate in the presence of random potential. It means that at time 0, the trap is switched off and the condensate starts expanding. The expansion is governed by the time-dependent Gross-Petevsky equation. So I'll be talking about this equation now. IH bar d psi dt equal to minus h square over 2m Laplacian psi plus nonlinear term well, that would be the free expansion, but I'll discuss expansion in the presence of the random potential. So somewhere all around the trap will switch on random potential. So V of r is this random potential. So it's a nonlinear Schrödinger equation in the presence of the random potential. Oh, it's switched off. Yes, the trapping potential is switched off, and the condensate goes and expand, but the random potential will be switched on.
So it's just to give you an initial state, right?
Exactly, yes. I have to solve this equation with the initial condition, which is written here. So initially, just to simplify the problem, we don't put any random potential in the trap. So this is the initial condition. And then the trap is switched off, the condensate expands, and the random potential will be switched on. But first I'll discuss, just to very, very briefly, the case of free expansion with no random potential. So this equation is it's of interest not only for Bose-Einstein condensates. For instance, it is well known in nonlinear optics. Maybe without this random term, but okay. So then there are some analogies between this Bose-Einstein condensate dynamics and nonlinear optics. Okay, so now I'm going to the PowerPoint. Well, I will use this stick because every time when I take this electronic pointer, I develop some symptoms of Parkinson's disease. I cannot focus this. Okay. So basically, I already covered this first slide, even in more detail, to give you some background. This time-dependent Schrödinger equation, nonlinear Gross-Petevsky time-dependent equation, can be rewritten in slightly different terms. Well, we can always write psi, this wave function, as square root n is the density of the condensate, times this phase. This is the dynamic phase. Initially, it is 0.
Boris, just before you go into this, what is the justification for remaining with Gross-Petevsky dynamics? after the fast switch? What controls the validity?
Yes, this is a subtle question, and I don't know whether it was really accurately studied. I think if you look at Leggett's review, he will write something like a condition that, well, 1 over omega, as I will show you, and now it's in the absence of disorder. The characteristic time, dynamic time for the condensate is 1 over the frequency of the trap. And this time should be sufficiently slow, so it should be larger than, actually even by dimensionless arguments, but by dimension arguments, I think the only time, relevant time we can write here is MA, but A is scattering length. That's the we have to compare this to some typical microscopic time. So I think that's what people usually write, but then it's at least consistent, because this is the same as, well, this is scattering length. This is the same as saying that the scattering length is much smaller than the oscillator length, right? H bar over m omega squared. But scattering length for this, in Gross-Petevsky, for any macroscopic description, it must be always assumed that the scattering length is smaller than all other relevant macroscopic length. That's the only condition I know, but probably it's more subtle than that.
Well, here we know that there's this rigorous work by Erbusch and company deriving Gross-Petevsky from a two-body Hamiltonian.
Time dynamics.
Yeah.
Time.
So we,
No, the question is about differences. The question is that after these condensates start to move,
Yeah,
you
yeah.
have particles overcompensate, and they may influence others. Why should we watch only condensate and don't think about the rest? This is a physical question. It is not a question about rigor.
On the other hand, in the rigorous derivation, there is a subtle question of on which time interval it is there.
Okay.
yeah, it's true they don't watch the particles outside the condensate, as far as I remember. So, in that sense, it's a valid question.
Yeah, but nevertheless, to know what is going on in this condensator is of interest. Why not? Maybe it is not.
At least, just before we, it's clear that you don't want to discuss any deviation from Gross-Petevsky.
No,
So
no.
before we leave you with your formula, could you say about your feeling, whether it is valid at initial stages of expansion, or it's valid at all stages of expansion? The criterion you brought does not know about density, right?
Yes, there is, of course, always the requirement that the interparticle distance is much larger than scattering length, which is this criterion. Density times scattering length. Well, this is the condition of sort of a almost ideal gas. So, but this is always satisfied with great accuracy in experiments, and even this condition becomes better.
The farther it is going, the better.
Yes, this condition.
Then non-linear term is getting less and less important.
Yes, but this I will discuss. Okay, so as I was saying, there is another way to write this time-dependent Gross-Petevsky in terms of density and phase or gradient of the phase, which is the velocity. Then it looks like some kind of hydrodynamic equation, continuity equation, and this is sort of Euler equation with this is kind of pressure. And these equations have now I'm discussing free expansion, no disorder. So I'm solving this Gross-Petayevsky time-dependent equation with the initial condition of inverted parabola. And this, well, these people know how to solve. There is kind of scaling. There is a self-similar solution. I write it here. So this is the density field, and this is the velocity field at any instant. B is the scaling factor, depends on time, but not on position. It is found from this equation. Again, b to the fourth, because I'm doing 3 dimension. In 2 dimension, it will be b to power 3, and then this equation can be solved analytically. But in any dimension, the picture is quite simple. There is a characteristic time 1 over omega, I denoted t naught, that for time smaller than this time t naught, the expansion is dominated by nonlinearity. It's sort of explosion. After this time, most of the energy stored in the interaction in nonlinearity is converted into flow, into the kinetic energy. So after that time, the expansion is, to good accuracy, is simply a linear evolution. Well, this box is, should be what I meant here. I don't know why it comes out this way. Sign of approximate equality or order of magnitude equality. You know, the sign which physicists use when they want to conceal some uncontrolled approximation. No, but in this case, it's this is the exact solution of these 2 equations. Simply, I split the time into 2 intervals. One interval smaller than t naught, then it's rapid explosion. After that time, it's linear evolution, but with the initial condition, which is written here. That's roughly how the wave function looks at time equal t0. So, okay, so for times larger than t0, it's a linear evolution. It can be seen from this. The velocity is simply proportional to the position divided by time. Okay, so all this is well understood, but now we switch to disorder. Maybe before writing equations, I will show you an experiment. So far, all experiments with disorder were made in 1 dimension, or it's quasi 1 dimension. It's not strictly 1-dimensional system, of course, because then it becomes what they call Girardot-Thom gas. But it's a narrow waveguide. Of course, all the potentials here are made with lasers. For atoms, they are neutral. The potential is made by a gradient of the light intensity. So they can confine tightly atoms. They can confine them tightly in transfer direction, kind of a waveguide. Well, at the beginning, it's confined in all 3 dimensions, but then they can release it in 1 dimension. That's what was done here. So it's a waveguide geometry. the measure of disorder, well, again, the disorder, the random potential is also made by lasers. It's what they call optical speckle, random pattern of light intensity. And the measure of disorder is this thing. It's root mean square value of the potential. This speckle potential, it's not similar at all to the say Gaussian or white noise potential that we usually use in our calculation. It has long range correlations. I will at the end comment on that. So this gamma is the measure of the strength of disorder. So the first panel, the first set of pictures is gamma equals 0. So this is the free expansion that I just described. So you see the condensate preserves. This is x-axis.
Longitudinal direction.
This is the longitudinal direction in which the condensate expands and the image is taken. The y-axis is the density of the condensate. So this is this function n of x at different times. They let the condensate expand for some time, then they take the image. So this is what I was showing you. It's basically the condensate preserves its shape of an inverted parabola, but it expands according to that self-similar solution that I showed you. Here there is some disorder. So disorder inhibits expansion to some extent. Here the disorder is stronger, gamma is 0.3, so practically the condensate does not expand. So this is not the very recent experiment. They have more recent experiments. Well, I don't know why exactly, but they are determined to see under localization in one dimension with this condensate, and they achieved it. Well, for that they want to make interaction as weak as possible, so they have to work with condensate with very, very dilute, only maybe 10,000, of the order of 10,000 of atoms. Well, but they're very proud that they saw now exponential decay of this wave function. Okay. So now I'm going back to this Gross-Pitayevsky equation with disorder. Now, I'll be doing something very simple. So as I told you at the beginning, the nonlinearity is very important. But after some time, after time of order 1 over omega, this what I call T naught, the energy, the interaction energy is converted into flow energy, and the evolution becomes essentially linear. So if I want to connect it to experiment, then it should be like that. First, release the condensate from the trap. Let it propagate for a time of order T naught. It will roughly double in size, but the wave function will develop rapid oscillation. It will become complex, and a lot of kinetic energy is now stored in this wave packet. But after that, you can study linear evolution. So after that time, we switch on the random potential, and the condensate propagates now in the random potential, but the evolution is linear. And all the nonlinearity went into this initial shape of the wave packet at time t0. Okay. Well, I will reset T naught, this time T naught back to 0. So now we're in business because it's linear Schrödinger equation with disorder. What is slightly unusual maybe is that this initial wave packet is, it's not the wave packets we mostly study, some kind of nice Gaussian. It has a lot of kinetic energy in it, a lot of rapid oscillations. And also in condensed matter, we mostly use to study wave functions at a Fermi energy. But here we have to study a wave packet with a broad spectral content and to see how it develops. Okay, so from now on I will be rather brief. So
Sorry, can I just again make sure I completely understand? So the linear equation has some stationary solutions, some fixed points. The linear. It's got eigen.
Yeah, it has stationary solution for a given realization of the
For a
random.
given realization of the disorder potential.
Yes.
Can I just understand, if you ask about the fixed point structure of the nonlinear, of the fully nonlinear problem, do I have the same density of fixed points? I don't recall what the answer was in Quasi 1D, but I am recalling what Spivak and Zuzin wrote on this problem, where you have this enormous manifold of fixed points, and it looked actually very different to the linear problem. And I'm just trying to understand what is the connection.
Yeah, I don't know. Spivak is using in context of the speckle potential at a given frequency.
But your beloved equation down on the bottom left is just the same one, of course.
Well, I think they consider some fixed frequency of the incoming light. Here it's a time-dependent problem. I don't know. I think the
potential does depend on T. Yeah, just you can create from speckles.
the potential
Then the potential
does not depend on time.
Yes, this is what I'm saying.
Yeah. Well, but that's not the issue. It's a stationary potential. Well, I think that some of the intuitive picture is that as this wave packet spreads, the nonlinearity becomes less and less important. So at the end, you should end up with linear evolution. But this is also controversial.
That's
like
controversial.
in the workshop, we heard
It's
about.
controversial.
Yes. I mean, the naive argument that if you get it spread enough, then the wave function, there is normalization, of course, which is preserved in time. The wave function should become small, and the nonlinearity should become not important. But I don't know. It's controversial.
But is that the argument that you're invoking for looking at the linear problems? Or it seemed that you were
For the
saying
linear
something
problem,
more,
no. For the linear problem, it is not controversial. In the absence of disorder, I showed you the full solution. It is, you can see that after time larger than this T naught, evolution is accurately described by linear evolution. So in principle, if you wait long enough and then switch on the disorder, I think you are safe, because even these people who argue about whether nonlinearity, even weak nonlinearity, can destroy, for instance, localization in one dimension. But I'm not doing one dimension at all, by the way. But even they agree that there is some threshold, that if nonlinearity is really weak, then it cannot destroy localization. There's some, if you start with localized states, then very weak nonlinearity, they are stable against very weak nonlinearity. But well, even this is not proven. But anyway, I'm not doing localized state. I don't want to do any. I'm not doing one-dimensional problem. I want to do 2 and 3 dimensions, diffusion.
Okay, but still,
Stuff like that.
just make sure I understand. You're invoking this approximation that the entry point of nonlinearity is only in the initial condition on the basis that the nonlinear term is small, or there's a stronger argument on top of that? Is it just that it's a small
Yes,
nonlinear
that
term?
after some time, after this initial stage of expansion is finished, and at that stage there's no disorder, or disorder is very weak. After that, nonlinearity only enters through this initial function. This function knows about nonlinearity, but the evolution, I study linear evolution. Okay.
So when you study this, you're studying it in 3D or 1D?
No, 3D or 2D, not 1D. What I'm talking here is 3D. So you can write this solution in terms of the green function, and then you want to study this evolution in time of the density. Again, okay, here it's again approximate equality. So it is, well, we know how to average green functions. In the case of weak disorder. But there are all kinds of scaling arguments. I will not go into this. All this was developed in the 80s. It is possible to transform. So you have a product of two green functions. You average, you define some kernel. I will write it explicitly at the next transparency. But this density of the condensate can be represented as an integral over density of states. This is the Fourier psi tilde k is the Fourier transform of this function, this inverted parabola with a lot of oscillations, and this is the main hero of this story, the transport kernel, quantum diffusion kernel. I will tell about it a bit. So this kernel, this is its definition, a product of two green functions averaged. And we know how to calculate it in the diffusive regime. Okay, so all this is based on this picture that if this is the energy axis, then somewhere there is the mobility edge. For energies, so here states are localized, here they are extended. And for energies much larger than the mobility edge, we have simple diffusion, and then this kernel is the diffusion kernel, but with kind of scaling arguments, we can extrapolate these results up to the mobility edge and even somewhat below. For instance, well, at the mobility edge, you have what is called anomalous diffusion. When the mobility edge is approached, the DC diffusion coefficient is going to 0, but one can introduce the frequency-dependent diffusion coefficient or frequency-dependent conductivity. For instance, below the mobility edge, this kernel has a well-defined time infinity limit. I'm sorry, here I missed psi square in the denominator. So I will not dwell on this. But show you some results. We studied it, we did this integral numerically. In some cases it can be done analytically. Let me only discuss, okay, so all this, again, all these boxes, here it's proportionality sign, the localization length close to the mobility edge is epsilon c minus epsilon to power minus nu. I'm only showing you the result of in the time infinity limit. So we have this initial wave packet, but it contains all kind of Fourier components. And after a long time, everything that could diffuse away diffuses away by any kind of diffusion, regular diffusion or anomalous diffusion. What is left? Only the localized part. So this is the picture. This condensate is released from the trap, and it diffuses most of it. It depends, of course, where is the chemical potential. I'm only discussing here chemical potential much larger than the mobility edge. Then most of the condensate diffuses away, but some fraction is stayed localized in the vicinity of the trap. I mean, of the initial trap. There is no trap anymore. So this is one of our results, that this is the fraction of the localized condensate. There is some function of this ratio epsilon c over mu, and it decays some power away from the trap. So this should be the shape of the condensate after a very long time, when most of it already diffused away. It is also possible to calculate the fraction of localized atoms just by integrating this expression. Of course, with a cutoff, because this expression only valid when R is much larger than the mean free path. So we have this is the result for the case when the chemical potential, the initial chemical potential in the trap is much larger than localization length. Then only a small fraction, epsilon c over mu to power 3/2, remains localized. The rest diffuses away. Well, maybe I will skip this because this is a different approach to how to calculate the number of localized atoms, or the fraction of the localized condensate. Let me skip this because I want to say a few words about fermions. So far it was Bose-Einstein condensate. But there are experiments with Fermi gases as well. So the same story. There is this the trap now filled with fermions.
There we have all those time-dependent Gilbert Landau is a wrong theory.
Yeah, but that with interactions. You mean with attractive interactions? Yeah, I will discuss non-interacting fermions.
We will discuss non-interacting. So it will be no condensate.
No. I'm not discussing BCS. I'm not discussing BCS. Now it's something. I switch gear. Something completely different. There are fermions. Well, with repulsive. They can control, by the way, interaction with the help of this Feshbach resonance. They can switch interaction from repulsive to attractive. Of course, not that interaction is something boring. I'm all for interactions, but in this context of disorder potential, first they want to understand non-interacting fermions. So, and in many cases, unlike BEC, that interactions in the trap are always very important, here this is not the case. The only interaction between, the most important interaction between atoms is S-wave scattering. If you have polarized Fermi gas, then as wave scattering is switched off, and very little interaction is left. So non-interacting Fermi gases, experimentally under some condition, it's a good model. And that's what I'm discussing now. Okay, so then the problem is conceptually very simple. You have initially this Fermi gas in the trap. There are random potential around the trap. Well, we can neglect the potential or simply not switch on the potential on the trap itself to simplify a bit the problem, to have a simpler initial condition. Then at some initial time the trap is switched off and the gas starts expanding in the presence of the random potential. So it's very easy to write down the basic equations. So simply every wave function evolves according to the Schrödinger equation. You only have to sum this expression. Well, you cannot do exactly the sum, but you can write this in the following general form. So this is the average density of this Fermi cloud at some later time. The structure of this equation is very simple. The first integral is, it contains the information about the state in the trap. So this green function refers to the green function for the Fermi gas in the trap, the small g. And this product of the large g, this is the transport. So this kernel takes this initial information from the trap to the distant points in space, and that what defines the average density. Well, this is not it can be studied. We studied it, but it's not a very interesting object. Let me concentrate on
I have a very naive question. How it could possibly that in the density you have three Green's functions?
Well,
You
again,
said that
this is
little g is also Green's function.
yeah, but this is, think of this little g, think as the initial wave function of the Fermi gas in the trap. So it's psi dot, psi star psi, something like that. Of phi, the initial, well, that's what you expect.
I would understand, but okay.
No, okay, but it's more clear.
It's for me,
Here it's, I guess it's more clear here. So the density is a product of two wave functions, but wave function, one wave function contains green functions and the initial wave packet. So you have two green functions and two initial wave packets. So this little g comes from summing this object. Maybe the last few minutes I'll spend on discussing a more interesting problem, the density-density correlation function. So even in the absence of disorder, when they take an image of this expanding Fermi cloud, the density is not homogeneous. It's a grainy picture. Simply, well, this is a purely quantum effect, which is related to anti-bunching of fermions. This point was particularly emphasized by Leggett and by Altman with co-workers, because when we calculate the average density, the quantum mechanical expectation value of the density of fermions, well, we obtain some structureless, some smooth function. For instance, if it's in a box, it will be just a constant, but in a harmonic trap, it will have some smooth behavior. But in a given experiment, when one image is taken, you do not measure the expectation value. Okay? For instance, if the resolution would have been infinite, then you would simply see a set of points. So therefore, in order to characterize the image, the picture that this grainy picture that they have an experiment, it's not enough to calculate the average, the expectation value, quantum mechanical expectation value of the density operator. You have to do the correlation function. This will give you an idea of how fast are these changes in space, fluctuations. So now this is the object to study. So there are quantum mechanical averages, and the overbar denotes averaging over disorder. Without disorder, this object, of course, is well known. To be more precise, what is well known is the density-density correlation function for Fermi gas in a box, in equilibrium. Here it's a bit different because we switch off the trap, the Fermi gas expands, and people study experimentally, and I want to compute this. The density-density correlation function at some time after the expansion. But in any case, this is the object to study, and this correlation function can be reduced to this consigns expression, where this f function is something similar to the average density that I showed you on the previous slide, but now there are 2 points, r and r prime. For r equal r prime, that would have been just the average particle density. Okay, so that's how this function looks for. So again, this box is the sign of approximate equality. So in 3 dimensions, and for distances larger than the initial size of this Fermi cloud, so we have to let it expand for a while, and then take the image. And okay, so it's convenient to normalize the correlation function to these average densities and at these 2 points, and this is the result. So there are oscillations on a scale of the Broglie wavelengths at the Fermi level, and I emphasize that this K Fermi is the Fermi wave number in the trap. So it's this result is a bit surprising that the clouds expands, the density drops, the average interparticle distance grows, but if you normalize the correlation function to this average distance at a given time, then there is no time-dependent quantities anymore on the right. This K Fermi refers to the wave number in the trap. And there is a similar result in 2 dimensions with Bessel functions instead of this sine function. Well, my last comment is concerns a somewhat different problem. Now assume that we have the initial, this is the initial equilibrium state of the atomic cloud. Here I again switched back to Bose-Einstein condensate, but what is done here is that the disorder, and possibly a strong disorder, is applied now directly on the trap. So it's a different kind of a problem. There is this harmonic trap now with disorder. So maybe already in equilibrium you have a complicated picture, maybe a fragmented Bose-Einstein condensate. Or if it's a smooth potential, then to a good approximation, the Thomas-Fermi picture applies. So you have modulations in the density. Now at time 0, all the potentials are switched off. And the condensate now executes free expansion, but with the initial wave function which is described by this problem. You can have, for instance, some localized you can have some localized states and localized part of the condensate extended already in the trap, and then the question how this wave function evolves in time, because well, usually in experiment it is very difficult to look into the trap. The initial size of the trap is maybe only 20, 30 microns, so there is not enough resolution. They don't like to have this imaging, what they call in situ. We have to let this cloud propagate for a while and then take the image. So it's kind of a, well, we have no results on this problem, just to define it. So it's a new kind of problem. Basically, to summarize, I want to say that these cold atomic gases, Fermi or Bose, expanding in the presence of disordered potential, they give us kind of new problems that we usually do not consider in condensed matter. Well, this is one of such problems, and at the end also, what is important that the speckle potential, the disordered potential, it has long-range correlations. It is of the following type. So this can also introduce some new features. Well, let me put here 0. You saw this equation, I think, in the talk of Garcia, perhaps somebody else. This is the correlation function for the random potential of this optical speckle kind. It's long range. So it's also an interesting question how things that we are now that we know with white noise or some short-range correlated Gaussian potential. Are there any changes when we come to this kind of long-range potentials? Even in the beginning, some people claim that you can have a mobility edge with this potential, but this I think is not in one dimension, because they were saying that such potential in one dimension, its Fourier transform is sort of a triangle. There are no Fourier components with well, K naught here is, by the way, the wave number of the light with which this potential is created. But anyway, such kind of potentials can have some additional interesting properties. Thank you very much.
Some questions or further comments?
It's very side comment. What I want to say is that we usually have three conserved quantities. One is number of particles, and you have continuity condition. Then you have momentum, and you have Euler equation. But plus to that, you have energy. And then it should be third equation. Somehow you're all the time speaking about zero temperature. And who said that after you switch off, you do prep? We did not heat up your gas, and how the energy is relaxing. There is no discussion of all this. And maybe you are right, and it is all irrelevant, but it still
Well, to start with,
leaves feeling of insecurity.
well, insecurity is a very positive quality in science.
Sorry?
To be anxious and insecure, it's very good in science.
But it's you.
Well, of course. No, but seriously, first, in the first place, this, of course, this Bose-Einstein condensate with cold atomic gases, it's a metastable, it is a metastable state.
That's exactly what I'm talking about.
But they know.
The rate of relaxation.
They know that, but
should be discussed.
it's of the order of seconds up to minutes. The
Right.
order of seconds, the lifetime of the condensate, it's even in the trap, it's simply a metastable because the true ground state of interacting, the true ground state at such temperatures, you know, we are talking here temperatures of micro or even nanokelvins. It's clear that it's a solid, but well, the mechanism for relaxation is three body collisions. This is because two atoms have to give their energy to the third atom. So the gas is very dilute. You can estimate this. It comes out in the range of many seconds, or even it depends on the density of the gas. Or with Fermi gas, there is no such a problem.
So I want to make sure I understood at least some of what you were saying. So you prepare the system in some state, maybe given by some nonlinear equation, and then you wait long enough, watch it relax, and then for the longer time asymptotics, you just use the linear random Schrodinger.
In dynamics.
Dynamic version of it. And then you want to see, let's say, what fraction of it is left over, and what fraction may actually
Diffuse away.
So of course the details of that will depend very heavily on the density of states, right? Below the mobility edge. You need to know how to compute that rather
Yes,
well.
it also depends it's very sensitive to the initial shape of the wave packet. For instance, you can control the bottom of the harmonic trap. You can put it below the average of this random potential. So you can have all kind of regimes. Yeah, this is in this first type of the problem. This type of the problem, it's something different. Here you switch off everything, so it expands. And then the question that by taking later the image, can you infer what was in the trap? Whether, for instance, it was a fragmented condensate because of disorder, or so this is a different problem. But that's always in big lines. This is the problem that experimentalists in this field encounter. They let the thing expand, then they take the image and they want to infer what was the state in the trap.
Coming back to the Bose problem, what actually is the final long-time distribution that you're predicting?
Distribution of density of atoms.
Well, I mean, you use the words that, you know, you have localized states, that
Yes.
trapped in these localized. The concrete question, exactly what is the nature of this distribution?
Well, in the long time limit, this is the equation. So n is the total number of atoms. Again, everything that could diffuse away already diffused away. And this is the long time stationary localized part of the condensate that you have. So it falls off as roughly fourth power. This exponent nu is it's 1.5. So that's how it falls away. This function, we know this function. It depends on the ratio. So the simplest case is when chemical potential is much larger than the mobility edge. Then,
But this average is made up of. If I unpack what this average is made up of, should I think of these as localized states of the single particle problem in which I've incorporated some condensate?
I'm not sure I understand the question. We are talking about
as you said, this is
condensate.
an ensemble average. So if I look at
Yes,
if
this
I look
is-
at a single realization of disorder,
well.
and what would I expect to
Yes.
see? That's what I'm.
In a single, I don't know. It's probably, well, this is probably not a self-averaging. It is not self-averaging quantity. For instance, if by chance you hit a realization where in the region of the trap there is a deep minimum, then maybe almost all atoms can stay there. Well, this is not a self-averaging quantity.
But experimentally, do you have only single realization? of
No,
this? Or
no.
you can average over.
It's very easy experimentally to produce, much easier than in our business, in condensed matter. In condensed matter, you have only one or maybe 3 samples. But here, every second they can reload the trap.
So they really can see averaged quantity more easily than.
Yes, because, well, first of all, I think, I'm not 100% sure that even with the same realization of the speckle potential, if you reload the trap, you effectively get a new realization because they cannot control the number of atoms in the trap very accurately. So the chemical potential will be fluctuating. So it's like having a new sample every time. But even to produce a new specular realization is also not a problem. So they have many samples.
I was puzzled by the last thing you said. I mean, I would have thought in these kind of things where you have trapped particles, you expand them in order primarily to get them at distances where you have optical resolution. That each experiment you do gives you the record of a single realization. You're not doing ensemble averages unless you choose to.
Of
You
course.
are taking pictures of one sample.
Yes.
What its instantaneous aspect is at the tiny farther laser end.
Yeah, that's true. Yeah, every single experiment is one image for a given
Is
realization.
one image for a given realization, and any averaging you do is done in your computer, not in your experiment.
Ah, no, no. Well, how with one experiment you can also do averaging, but then you have to average over space somehow, assuming some ergodicity. No, but you simply make many experiments. That's what they do. They reload the trap again, and they take another image, let it expand for exactly the same time, and so they can have many images. It's not.
Yeah, but that's very different from what's done in most condensed matter experiments, where a single experiment involves multiple.
Yes, but well, it's also not a single experiment. Like for instance, with universal conductance fluctuations, for instance, or whatever. We have maybe only one sample, but then we tune the magnetic field, and in this way we create an ensemble of samples, which. Yeah, but in their case it's much more straightforward because they simply reload the trap and again do it again and again, as many times as they want.
Yeah, so, Boris, again?